This module is an introduction to a new kind of statistic called a t-test. A t-test is very similar to what we've been learning about in previous modules, where we were using a z-score to go through the process of a hypothesis test. But this time we're going to compute a new kind of statistic called a t and go through the same hypothesis test process that we were using before, with just this slightly modified statistic. This module is going to deal with what's called a single sample t-test. In future modules, you're going to draw multiple samples from a population and compare them to each other. But in this module, we're just drawing one single sample from the population and comparing it to the population. So that's why it's called a single sample. Here at the outset, I want to let you know what my learning outcomes are, what I hope that you'll master by the time this module is finished. The first thing is you need to know when to use a t-statistic instead of the same z-score hypothesis test that we were using in the last module. The second thing you need to know is when to perform a hypothesis test with t-statistics and how to do that process. And the third thing is to be able to evaluate the effect size of some treatment by computing Cohen's d and a percentage of variance accounted for, that's known as r squared, and a confidence interval. In any given situation, you might not compute all three, but you need to be able to know how to compute all three so that when I ask you to do one or the other, you'll be able to compute it and understand how to interpret what's going on there. So, here at the outset, I need to explain why are we even doing this t thing instead of just keeping using the z? Well, the problem with z-scores is that they require more information than researchers typically have available. For example, they require you to know the population standard deviation. But sometimes we only know the mean and not the standard deviation. So, a t-statistic is an alternative to a z. When you don't know the population standard deviation, then you can use the t instead. Thus, a t might be considered an approximate z. It's like a way of estimating or guessing what the z might be if we did know the population standard deviation. And it's really very simple. We just use the exact same formula that we used when we were computing a t. We just replace the sample standard error with the population standard error. And so it looks like this. Instead of using the sigma sub m, which represents the population standard deviation, standard error of the mean, then we use instead this italicized lowercase s, which means the sample standard deviation, and this is the sample standard error of the mean, so it looks like this. Watch, wait for it. So you can see here that this sigma, what used to be there before, has been replaced by a little lowercase italicized s. The sigma used to represent the population standard deviation, but this little italicized s represents the sample standard deviation. And by replacing the sample standard deviation here and dividing it by the square root of n, we're just using the sample to guess what we think the population standard deviation might be using the information that we have access to in our sample. Because most of the time in real life, you cannot measure an entire population of people. It's just too big. If you want to know something about all the people in the United States, you cannot measure all of their height or all of their weight, but you can draw a sample, and you can use that sample to see how variable people are in general, and then guess how much the variability in the population is based on the sample standard deviation. And so if you make this correction, if you do the standard deviation divided by the square root of n, then that is that's an estimated standard error of the mean, an estimated standard error. So all we've done here is we've taken the old standard error that was computed from a known population standard deviation, and we're guessing what we think it might be based on the sample standard deviation. And so what this represents here, if you recall, is the standard deviation of the sampling distribution. If you have a population and you draw sample after sample after sample after sample, and for each one of those you compute the mean and you plot it where it lands, that new distribution will have less variability, it will be less wide apart than the population originally was. By how much? By dividing by the square root of n. That's the correction that we make that allows us to say how wide the sampling distribution is. Now the t-statistic is just exactly like a z-score that's using the estimated standard error in place of the standard error of the mean computed based on the population. Here on the bottom of the equation you can see that we've used the estimated standard error instead of the actual standard error of the mean, but the top of the equation is just like you'd see in a z-score. The z-score formula was the mean of the sample minus the mean of the population, how far apart they were, divided by the standard error of the mean, how far you expect them to be, typically just by chance. And so we were comparing how far apart they are versus how far apart we expect them typically to be just by chance to see if this is very big far apart or very small far apart. But this right here is just the same as a z-score. We just have replaced an estimate here instead of the actual known population standard error of the mean. So the t-statistic is used to test hypotheses about an unknown population mean. Usually this is like a treated population, that you don't know what happened to the population after you've treated them, when you also don't know the value of the standard deviation of the population. Now before we move on, I just need to give you a brief refresher. Remember about the principle of degrees of freedom, that in order to compute a sample's variance, you have to first compute the sample's mean, and then this means that only n-1 scores in a sample are independent or free to vary, because once you've computed the sample mean, you've already used the sample to fix one of the scores. Once you know the sample's mean, then one of the scores is not free to vary. It has to be, the last score has to be a certain value in order to arrive at that sample mean. So the degrees of freedom are n-1. Researchers call that principle the degrees of freedom, and we abbreviate it df. We're going to use this degrees of freedom multiple times as we go throughout the rest of this presentation. Okay. Z-score distributions are a plot of all of the sample means that you could possibly have in a normal distribution shape once every single one of those have been computed into a z-score. And you remember, once you've computed a z-score, the average is 0 and the standard deviation is 1. And if you create a sampling distribution and graph all of those, you then end up with this shape here that's called a z-distribution. Your table, B.1, is the proportions underneath the curve for any z value. If you picked a z of 2.2, you could figure out what percentage is under the curve beyond that point in the tail. All right. In this chapter, we're going to be using what are called distributions of the t-statistic. Very similar, but the t-distribution has some interesting characteristics. They are flatter than the normal distribution, and they're more spread out than the normal distribution, and they have more variability. That is, they have fatter tails. More of the scores are out in the tails in a t-distribution. So I'm going to go back to the last slide so you can see again how tall a z-distribution is. This is an actual normal curve, and a t-distribution is not quite normal. It's nearly normal, but it's a little too spread apart to be a little too spread out to be normal. These tails are a little too fat to be normal. Now, admittedly, I have exaggerated this shape quite a bit for dramatic effect, but the principle here stands that the t-distribution is a slightly different shape than the z-distribution was. Now I want to explain why this happens. The reason for these oddities is this. All the z-scores have the same standard error in the denominator. If you look here, the standard error of the mean is computed from the population variance. And so this ends up being the same every single sample you take from the population. You recall that this is computed by taking the standard deviation of the population, dividing it by the square root of n, but this right here is fixed. In every sample you take from a population with a known standard deviation, this is always going to be the same. And because your n size is also always the same, the standard error of the mean is always going to be the same. However, the denominator of a t-statistic varies from one sample to the next because the sample variance is different each time. So remember, the t-score formula looks like this. It's the mean minus the mu, same as the z-score, but we're dividing it by the estimated standard error of the mean. And because this is computed by the sample standard deviation divided by the square root of n, this will change every single sample you draw. The mean will be different in every single sample, and the standard deviation will be different in every single sample. So, when you compute a z-score, only the mean, only the sample means will vary. This and this will always be the same for sample after sample after sample after sample. But when you compute a t, it means that we don't know the population mean. We don't know the population standard deviation, and so this is going to be an estimate of the population standard deviation. This will vary every single time, which means this will vary every single time, and the mean of every sample will vary. And so the top of the formula, the numerator of the formula is going to vary, but also the denominator of the t-score is going to vary. And because both of those vary, that increases the variability or the spread outness of the scores in this distribution. In fact, there isn't even a single t-distribution. It's actually a family of distributions. There's one distribution shape for each value of degrees of freedom. So in this schematic here, you can see that a t-distribution with low degrees of freedom, like 5, has a very short, flat, see the bold line here, distribution with very tall tails, lots of scores in the tails out here. You can see how many scores would fit in the tails. But if you have a t-distribution with a higher degrees of freedom, like 20, then it's a bit taller, more of the scores are in the middle of the distribution, and fewer of them are out in the tails underneath this first dotted line. And if you have an actual normal distribution, then those are the tallest of all the distributions. Most of the scores are here in the center, a few, just barely any scores out here in the tails. This is table B.2, the table that hopefully you've downloaded and have access to. Maybe you've already printed it before you started reading this module. I want to go over the structure of this table so that we can use it as we go through problems working forward through the rest of the module. So you can see here this picture shows what one tail means. You either have a tail on the right or the left, and it's marking off the proportion of scores that fall in the tail of the distribution. If you have two tails combined, that means you have an equal portion in one tail and in the other tail. Now, the two headers of this table reflect the two graphs that are shown here, one tail versus two tails. So you can see it says proportion in one tail versus the proportion in two tails combined. So if you have a particular situation where you've marked off a critical region here and you want to say, I'm looking for scores that are in the top 5% of the distribution, the top 5%, then you would come down here and you would say, okay, I'm looking for the proportion that's 5%, not 10%, not 2.5%, but 5% in one tail. So in one tail, we've got 5%, and then you would come down this column and you would say, what are my degrees of freedom in this situation? And you would find whichever value depending on the degrees of freedom you've got. And you would use that as your critical T. If you have an alpha where you're using two tails combined, meaning you're using a hypothesis test that's not directional, where you're asking, is there a difference between this treated sample versus the population? And it could be higher or it could be lower, and we're fine if it lands in either the upper end or the lower end. We might also say, okay, let's take that 5% and we'll distribute it equally across the lower end and the upper end, which means that we would say, oh, it's actually 2.5% in each tail, because if you take that 5% and you divide it in two, it's 2.5% in each tail. But what the way this so that's what we had done in the Z distribution. We had to mentally say, okay, we're putting 2.5% in this tail. But in this table, it's already done the work for us. We're just saying the proportion in the two tails combined is 5%. So we find this here, 5%. And if we're using this situation with an alpha of 0.05 with 5% in the two tails combined, then we would come down this column here and we would just look for the degrees of freedom that matches the situation we're in. Okay, so just as we used the unit normal table, that z-score table, to find the probability that was associated with obtaining a certain z-score, we're now going to use a t-distribution table, B.2. So consider a t-distribution with degrees of freedom equal to 3. Find the t-score in the far right tail associated with the highest 5%. If you come down to this table, you can see that again, we're looking for a far right tail, so that's in one tail associated with the highest 5%. We would come down to the proportion in one tail, find the 5%, and then because it's degrees of freedom 3, we follow this column down until we hit degrees of freedom 3. We've highlighted it for you already. The t-score that's associated with 5% in one tail is 2.353. Let's work through another example. Let's consider a t-distribution with a degrees of freedom 4. What would be the t-score that's separating the far left tail, where the lowest 1% of scores lie? So let's come back up here. Proportion in one tail. We're looking for 1%. If you scan these numbers, you'll see here 0.01, 1%. We follow this column down until we get the degrees of freedom 4. As you can see here, degrees of freedom 4. So we've landed at a t's value of 3.747. But because this is the lowest 1% in the left tail, we have to say, oh, this is actually a negative 3.747 that we're looking for. Now you need to note here that this table I've given you, B.2, has been abbreviated, so the proportions for a t-distribution with degrees of freedom 40 is listed, and the one with degrees of freedom 60 is listed. If you look at your table, you'll see that, but none of the ones in between. It just skips from 40 to 60. So if your t-statistic had like degrees of freedom 53, for instance, then you would just need to look up the critical t and use the larger one because it's more conservative. Usually that'll be the one with the lower degrees of freedom, but you don't have to remember that. Just look up both degrees of freedom 40 and degrees of freedom 60 and use the larger critical t because it will be harder for the sample mean to fall in the critical region if the critical t is larger. As a reminder, the basic situation that we're replicating here in every given research paradigm is we have a known population before treatment. It has some mean of 30, and we take the whole population, give it a treatment, and we have some unknown population after treatment. This will have a mean of 30 if the treatment was useless, or it might be higher than 30 or lower than 30. If the treatment was beneficial or harmful, then it will have increased or decreased the mean of the whole population. But as I've said before, we never really do this. We can't draw the whole population and treat everybody. Instead, we draw samples from the population and we treat them. The amazing thing about a t-test is that you don't actually have to know what the population was before treatment. In this example, we've we've imagined a situation where we know that the mean was 30, but we don't actually have to know that. You can compare a post-treatment sample against any number. That number could be derived from the population mean like this, but it could also come from a theory or a logical prediction or something. So I'm going to show you in an example what that might look like. So here's the example that we're going to be working through for the rest of the module. Infants have been shown in previous research to prefer looking at attractive faces. In one study, infants less than a week old were shown photos of 2 women, and prior to the experiment, adults had rated one of them as clearly more attractive than the other. The photos might have looked like this. This is a clearly more attractive woman than this, but this isn't actually a photograph of a woman. What this is a prototypical female face. So a computer algorithm took a bunch of attractive female faces and averaged them together using an algorithm to create a prototypical or an average attractive female face. And they did the same thing with a bunch of pictures of relatively less attractive women. And so when the infants were presented with these 2 faces, the 2 photos stayed on a computer screen until the infants had looked at them for a total of 20 seconds. Now, you can imagine for a second that if the infants didn't care about the difference between the faces, then they might stare at both of the faces just bouncing back and forth. And if you look at them for a total of 20 seconds, it might be an average. It might not be exactly 10 seconds per face for each infant, but the average should be about 10 seconds for the first face and 10 seconds for the second face. It might be like 2 seconds here, 2 seconds there, 3, 2, 2, back and forth, but it should add up to about 10 seconds per face if they don't have a preference. But if they like looking at the attractive faces more, then they should spend more than 10 seconds looking at that and less than 10 seconds looking at the less attractive faces. So let's suppose that we did a study that used 9 infants, and the average time that was spent looking at the attractive faces was a mean of 13 seconds. Now, I'm already going to just give you the sum of squares here as 72 for the sake of time, but you know how to compute this, and in some future problems I'm going to ask you to compute again the sum of squares, but just for expediency here, I'm going to give it to you. The first thing we need to do is find the standard deviation of this sample. Remember that we can do that by computing the sum of squares over the degrees of freedom and take the square root of that. That's the standard deviation of the sample. So we take the sum of squares, 72. The degrees of freedom is the n size minus 1. That's 8. And then we take the square root of 72 divided by 8. That is 3. So the standard deviation, how far apart the scores of the infants typically varied from each other, was about 3 seconds. So some infants, on average, spent 13 seconds looking at the face, but some were maybe up to 16 seconds or even 19 seconds staring at the attractive face, and some few infants were less than 13, maybe 10 seconds or 7 seconds, but on average they were about 13 with a standard deviation of 3. So the first thing we need to do, if you remember back to our last module where we learned about hypothesis testing, is to first state the null and alternative hypotheses. The null hypothesis is that infants have no preference for either type of face. There's no difference. There's no effect of being attractive or not. So they should spend about 10 seconds looking at each face. The alternative hypothesis is that there is a difference in how long the infants spend looking at the faces, so that they should spend more than 10 seconds or less than 10 seconds looking at the attractive face, something different than 10. So if we were going to write those in statistical notation, we would write H sub O for null hypothesis is that the mean of the attractive faces, the mean time spent looking at attractive faces, is equal to 10 seconds if there's no difference. And that would look like this. If you had a population and the average time spent looking at attractive faces was equal to 10 seconds. The alternative hypothesis is that the mean time spent looking at attractive faces was not equal to 10 seconds, something other than 10 seconds. So that would be like this. It might be higher than 10 seconds or lower than 10 seconds, but the mean of this population of time spent looking at attractive faces should be something other than 10. Now I've just, you'll notice that through the module, I'm going to keep up here in the right-hand corner some pieces of information that I've already given you or that we've already computed. And so here we know from the problem that the n was 9, the mean was 13 seconds, and the sum of squares was 72. We computed the standard deviation as 3. So we've just got those stored up there in the corner for us to use as needed. Step 2 of the hypothesis test. We have to set an alpha level and locate the critical region using the t-distribution table and the degrees of freedom. So you recall that we have a population. It has some standard deviation, but we don't know what it is. The mean time spent looking at the faces will be 10 seconds, but in order to guess what the population standard deviation is likely to be, we are going to have to do the same thing we did before and estimate it based on the standard deviation of the sample. Once we do that, which we've already computed the standard deviation of the sample as 3. Once we do that, then we can compute a sampling distribution, which is if we took sample after sample after sample after sample after sample of 9, and we computed the mean for each one, and we plotted it down here, and then we computed what's the mean and what's the standard deviation of this sample, it would be a mean of what? 10, still the same, because the mean of the sampling distribution is always the same as the mean of the population. But the standard deviation of the sampling distribution is the standard deviation divided by the square root of n, right? Do you remember that? Standard deviation divided by the square root of n. But because we don't know the standard deviation of the population, we have to use this sample standard deviation to kind of guess what we think it is. And we'll take that standard deviation there, divided by the square root of n, and that is 3 divided by square root of 9, or 1. So there we put the standard error of the mean. I'm just going to log that up in the upper corner so that we have it in our memories. But the standard error of the mean is 1. That's the distance here. We transform the entire sampling distribution into t-scores. We've done this before, transforming everything into z-scores, but now we're computing it into into t-scores because we don't know the population standard deviation. And once we've transformed all of them into t-scores, the mean should be, just like in z-scores, the mean will be 0, and the standard deviation will be 1. So this is now the sampling distribution computed into a standardized distribution with a mean of 0, standard deviation of 1, and we're going to stick with convention, put our alpha at 0.05. Sometimes it might be higher or lower or something like that, but this time we're just going to use the typical alpha of 0.05, and for this sample our degrees of freedom, n minus 1. Remember n was 9, so n minus 1 is 8. We're going to look at the t-distribution table for a two-tailed test with an alpha of 0.05 and degrees of freedom of 8. Take a moment, look at your table, and see if you can figure out what is the t-value for our critical regions that separate out the 5% combined in both tails. So there should be a combined 5% that land in the tails of this distribution. What are the t-scores that separate that outer region and that outer region? Hopefully you were able to do this and you recognize that the degrees of freedom was 8 if you follow that row across until you arrive at the place where it says the proportion in two tails combined, that is 5%. You'd follow that column down and you'd arrive at this one that says 2.306. But because we have an upper limit, a t up here, and a lower limit, a t down here, we have to recognize that that's both positive and negative 2.306. Okay, so this is the same slide I showed you before, but we just have to label here that what's going on is we have a negative 2.306 and a positive 2.306, and if our sample mean that we draw from this population lands in this tail or in this tail, then we probably, it's most probable that the treatment worked. In this case, it's not really an external treatment that somebody gave, but the independent variable that we're interested in is attractiveness of faces. So the attractiveness of faces worked and caused the infants to stare longer at attractive faces than less attractive faces if it lands in this upper region. If it lands in this lower region, that means that they spent less time looking at attractive faces, and that means that they actually prefer ugly faces. Alright, so we've done the first two steps of a hypothesis test. This is step 3, calculate the t-statistic. Now, the first thing you need to do is just go to your formula table and look up the formula for a t-statistic. If you already know everything you need to be able to compute this, that's great. So far, we've computed the mean as that was given to us of 13 seconds. We've stored it up here in the corner. The mean of the population, if the null hypothesis is true, is 10 seconds, and so we would take the 13 minus 10. But whenever you're working through a formula, if you land at something that well, we actually did already compute this, but I want to teach you a principle here. If you land at a component of a formula that you haven't yet computed or that you don't know the answer to, just look up that component of the formula in your formula sheet and find what that is. So in order to figure out the standard error of the mean from a sample, we have to just compute the standard deviation and the square root of n. And in order to compute the standard deviation, you have to compute the square root of the sum of squares over degrees of freedom. So in order to compute this t, we have to compute the standard deviation and the standard error of the mean, and then we have to compute the t. So there's kind of like multiple steps that go into it. We've already computed the standard deviation, but I just want to remind you that that's 3 and that's how you compute it. We've calculated the standard error before, but I just want to remind you again, it's 1. That's how you compute it. But then we finally put these components into the t-statistic. We take that 13 minus 10, and we put it over the standard error of the mean, that's 1. And you can see here that the t is 3.00. So, this fourth step of the hypothesis test, finally, we make a decision regarding the null hypothesis. The obtained t-statistic of 3 falls into the critical region that we've outlined. So we said our lower limit is negative 2.3, our upper limit is positive 2.3. If we plot that t-statistic, it lands right here. This is the sample mean, computed into a t-statistic form. Since it falls into the critical region on the right-hand side of the distribution, should we reject the null or fail to reject the null? Remember, if it falls in the critical region, we reject the null hypothesis. And we write a sentence like, our data suggest that babies will spend more time looking at attractive faces, comma, t equals 3, comma, p less than 0.05. There are some assumptions associated with the t-test. The math underlying the t-test requires that we make the assumption first that the values in the sample are independent observations. We've talked about what that means before. It means that the individual observations are not related to each other in some familial fashion, but also in any other fashion. Like they don't all go to the same preschool, or they don't all, I don't know, they're not related in some fashion, that we've independently pulled them from the population of interest. And also that the population sampled has to be normal. But, as we learned before in a previous module, with large samples, this assumption can be violated without really affecting the validity of the hypothesis test, because when you draw a bunch of samples, when you draw a bunch of samples to create a sampling distribution, and you have large samples in a large n size in each of those samples, then your sampling distribution ends up being normal shaped even if the population isn't normal shaped. So it's okay if your sampling distribution is normal shaped, even if your population isn't. Then you've still met that assumption. All right. A hypothesis test, like what we just did with computing that t and figuring out whether to reject the null, that only determines whether the treatment effect is greater than chance. But there's no measure of the size of the effect included in that test. And so a very small treatment effect could be statistically significant, especially with very large sample sizes, even if it's not practically significant. Even if it, like in this case, does it matter that infants spend 3 extra seconds looking at the attractive face on average? Is that big, small? It seems like only a few seconds, but in order to understand whether it's a big difference or a small difference, we have to compute a measure of effect size. Measures of effect sizes are not influenced by sample size, and so even if you grab a large sample of people and you compute a statistically significant result, it could be a very tiny result, but the effect size measure, because it's not influenced by sample size, is going to tell you what its actual size is, independent of how big your sample is. Now, we taught you in the last module about Cohen's d. Remember, the original equation included the population parameters, the known population standard deviation. We're going to use an estimated Cohen's d in this module, just like we've used an estimated t, which is the same as a z, it's just estimated. And we've estimated the population standard deviation based on the sample standard deviation. So we've done a lot of estimating based on the sample standard deviation, and we're going to do the same thing here. So an estimated d is the same as a regular Cohen's d, which is the mean minus mu divided by, and here's the difference, the population Cohen's d used to have a sigma here, a population standard deviation, but here we're just replacing that with a little s to say the sample standard deviation is used to estimate what the population standard deviation would have been. So notice that none of these components is heavily dependent on the sample size. This does have a little n used to compute it somewhere, but it doesn't have a heavy influence over the size of the standard deviation. And so this formula right here is mostly independent of sample size and will tell you about how big the effect is, regardless of how big your sample is. Now, it's important that you remember at this point that we can interpret a Cohen's d in words to mean the size of the difference in the standard deviation units between the treated group and the untreated population. So we're taking the treated group and the untreated population, figuring out how far apart they are, the difference between them, and then we're dividing it by the standard deviation. So we're saying that this is the number of units they are apart in terms of standard deviation units. So if you compute a Cohen's d, you could say, like if it was 0.5, you would say this is a half of a standard deviation, larger or smaller than you would expect it to be. So, from our example, remember we have these babies, they're looking at attractive faces for 13 seconds out of the 20, and we expect that if there was no preference, like the null hypothesis would predict, then the population mean would be 10 seconds. And so, in order to plug that into the formula, we say 13 minus 10. We divide it by the standard deviation we've computed before, that was 3, and we get an estimated d of 1. Now, the way we interpret that 1 is we say the infants who looked at attractive faces looked at them for one standard deviation longer than we would expect them to if they didn't have a preference for attractive faces. So they looked at it for 1 standard deviation longer than they otherwise would if the null were true. Now, we have to know, is that small, medium, large? What size is that? You'll recall from our previous module that I gave you this table with guidelines. Cohen's d that's considered small is around 0.2. It might be a little lower, a little higher, but it's around 0.2 and we consider that small. Something around 0.5 is medium, and something around 0.8 is large. Something much bigger than 0.8, like 1, that's much bigger than 0.8, and so we would say that's a large. In fact, it's quite large. If you had an even larger d, then you might say it's enormous, but you can use this table to kind of guide how big a Cohen's d is. Now there's a second way of measuring effect size. The Cohen's d was one way. That's a way of kind of independently saying, does this effect matter? I mean, they're looking at the faces for 3 extra seconds, but is that a small difference, a big difference? And in this case, we found Cohen's d said, wow, actually those 3 seconds were huge. You wouldn't think 3 seconds is a lot, but that's a lot more than you would expect it to be just by chance. And so here, we've got another way of measuring effect size, and that's called the percentage of variance explained. What we're doing here is determining the amount of variability in scores that's explained by the treatment effect, and we're using that as an alternative method for measuring effect size. So remember what variability is. It's the differences in scores. So like some people looked at the attractive faces for 13 seconds, some for 17, some for 8, but you can see that like there's differences across the infants and how long they spent looking at the faces. That's variability. Now, some of that variability is because of the treatment effect, or the independent variable, the fact that the faces are attractive in this example. So some of it's because the faces are attractive, but some of it's just because some infants are different than others. Some infants have more of a preference for attractive faces, and some have less of a preference for attractive faces. But those differences are just individual differences across the infants. This might be because of genes, or because of the particular attractiveness of their mother, or because of I don't know, the oatmeal they ate for breakfast. I don't know what it might be, but you can see that the differences between these infants could be because of 2 reasons. One is because of the attractiveness of the faces, and the other could be because of stuff going on inside the infant, the individual differences that make these scores all different from each other. So what we've got here is 2 graphs that have the same layout of scores. Notice this block of 4, this single score, this block of 2. This is also a block of 4, a block of 1, just a block of 2. Okay, that same distribution is centered here around the mean of 13, which is the actual mean of our sample. But we know that the mean of 10 would be if there was no treatment effect. We would expect to find that the infants would stare at the attractive faces for just 10 seconds. And here we're looking at how far apart are each of these scores in this sample from this null hypothesis mean of 10. So this first one is 2 units away. The second one is 0 units away. The third score is 2 units away. This one's also 2 units away. This is 3 units away. This is also 3 units away. This is 5 units away, 7 units away, and 7 units away. If you add up all that variability, that's the variability that's because of both the treatment effect and the individual differences. So this exists here as the treatment effect surrounding 13 and the individual differences across the participants, so everybody's at a different place. This is all the variability that exists in the scores. But if we wanted to take out the variability that was caused by the treatment, that's a 3-point treatment effect between the point where 10 is and the point where 13 is. The treatment effect is they looked at attractive faces 3 seconds longer. So if you take each of those scores and you subtract 3, you shift the whole distribution 3 points to the left, so that now this score these 2 scores that were on 13 are now on 10, and the scores that were everywhere else are 3 points lower than they used to be. Now you can figure out what is the variability when you're ignoring the treatment effect. So none of the variability here anymore is because of the treatment effect. All of the differences here between this point and the mean, this point and the mean, this point, all of these scores and the mean, the differences there are all due to individual differences in genes and attractiveness of mothers and breakfast eating and whatever else is causing differences. These infants are all different from each other now without any treatment effect involved. And so what we have here is an opportunity to figure out what's the variability in the first group. Well, it's the same group, but in the first set of scores where we're including all the variability because of individual differences and because of the 3-point treatment effect, and we figure out how much are these scores deviating from the null hypothesis mean of 10, and we compute, just like I said, this is 2 points lower, this is 2 points higher, this is 0 points away. We've got 2 points lower, 0 points away, 2 points higher, 2 points higher, and so on. And we square each one, and then we add up that variability. The sum of squares for this group is 153. But if we take out that 3-point treatment effect, and we then compute the difference of each of these scores from the mean of 10, then right now we've got, originally we just had a score of 8, and the difference between 8 and 10 was -2, but here we've subtracted that 3-point treatment effect. And we've said, okay, now the score is artificially lowered to 5. This one is artificially lowered to 7. This one, these two here are artificially lowered 3 points to 9. So you can see 12 minus 3 is 9. We've artificially lowered them, and then we compute the sum of squares based on that. And this is the sum of squares that reflects only the individual differences between the infants without any consideration of the treatment effect. Now, when we have the difference here between 153 and 72, what that tells us is if we take the total amount and we subtract out all the individual differences, 153 minus 72 is 81. 81 is the amount of variability that we've accounted for because of our treatment. It's the amount of variability in the scores that is due to the treatment. And you can then take that and divide it by the total variability. That's 153, because remember, this first set of variability was all the infants, was all the variability because of the individual differences among the infants and the variability that was due to the treatment itself, the attractiveness of the faces. And you take that total variability and you put it as the denominator, and if you divide that out, then 0.5294 is the answer in this situation, and that's 52.94% of the variability that's total in the infants was accounted for or explained by the treatment effect, that is, in this case, the attractiveness of the faces that they're looking at. Now, I recognize that that's a very difficult explanation, that the last two slides are probably counterintuitive, probably really hard to wrap your mind around. So I want to just put your mind at ease and tell you it's okay if you didn't quite get it. Mostly what you need to know going forward is that R squared represents a proportion of the variability that has been accounted for by the treatment. And there's a simpler way to compute it than to have to go through all that rigmarole and steps that I just showed you. You're never going to have to go through those steps that I just showed you. If it conceptually helped you, great. If it didn't, let it go. It's okay. Because what you need to know is that in order to compute this R squared, you can simply do T squared over T squared plus the degrees of freedom. And that will allow you to figure out how much variability is accounted for by the treatment effect. In this case, it's 53%. Now, here is a table that shows you how to interpret the size of that R squared. A 0.01 or 1% of variability is small. 0.09 or accounting for 9% of variability is medium, and 0.25 or 25% of the variability accounted for by your treatment effect is large. So if you compare this value, we've accounted for 53% of the variance. If you compare it against this table, you'll see that 53% is very large. It's much, much larger than even what we consider large. So you could say that's actually enormous. That's very, very big to have computed for 53% of the variability in infants staring at faces, and to say that 53% of the time that's spent staring at faces can be accounted for by how attractive the faces are. So whenever you have an effect size like Cohen's d or r squared, I need you to be able to interpret the effect size in terms of what it really means and in terms of how large it is. So in this case, the 53% can be interpreted both by size, how large it is, it's very large, as well as by what it really means. And in this case, it means that 53% of the variability in the infant's looking times is accounted for by the attractiveness of the faces. To give you kind of like a formula for interpreting the r squared, you would say x% of this dependent variable is accounted for by the independent variable. That's how you can always interpret it correctly. X% of the dependent variable is accounted for by the independent variable. Now there's another way of computing effect sizes that's called the confidence intervals. This is an alternative technique for describing effect size that estimates the actual population mean based on the sample mean. However, confidence intervals cannot replace Cohen's d or r squared because they're too different. This is a measure of effect size. Confidence intervals is a measure of effect size, but it's so different from Cohen's d or r squared that you really ought to compute both either Cohen's d or r squared and the confidence intervals. So confidence intervals are based on the reasonable assumption that the mean of the sample should be near to the mean of the population. In your sampling distribution, it won't always land exactly on the mean of the population, but it will hopefully be close. So the interval that you're computing here, the confidence interval, the interval meaning a range, the range of values, the interval that you're constructing here, defines what near means based on the estimated standard error of the mean. So we're using the same standard error of the mean that we've been using all chapter, and we're going to use that to define what is near. We can then confidently estimate that the mean of the population should be located inside the interval we've computed. So, just to give an illustration of what it is we're doing, remember from previous modules that we have populations from which we can draw sample after sample after sample after sample, and we compute a mean for each one, and we create the sampling distribution down here. And when we do that, the mean of the sampling distribution is equal to the mean of the population. But if you draw any given sample, the mean of that sample might not be the same as the mean of the population. So for instance, if I draw this sample right here, the sample mean for that sample was a couple points higher than the actual population mean. Now, if we say, if we draft out the range of values that is like -2 standard deviations below the mean and +2 standard deviations above the mean, then we can say about 95% of means fall in this range between those two values. But if we draw a particular mean like this, and I compute the range around that mean, then I can say with similar confidence that the mean of the population, which we usually don't know when we've computed a sample statistic here, will probably fall within this same range. This bracket is the same distance apart as the first one that I showed you. So if we can figure out what's 2 standard deviations below the actual mean of the population and 2 standard deviations above the mean of the actual population, then we should also be able to figure out what's 2 standard deviations below this mean of the sample and 2 standard deviations above the mean of that sample. And then we should be able to say the mean of the population isn't known, but it's probably somewhere a little below or a little above this sample mean. And so in this situation, you can see that the population mean right there actually is within that range. Every once in a while, you might draw a sample that's way out here. And if you do, then the red bracket might not encompass the actual population mean. But if this is a 95% confidence interval, that means that 95 out of 100 samples that you draw from this population and put into this sampling distribution will include in this confidence interval the actual population mean. They will, like, see how it's inside the red bracket now? This is the population mean. It's inside the red bracket, and that means the red bracket, the confidence interval, includes the population mean. And 95% of the time, when you compute, when you use a mean to compute a confidence interval, 95% of the time, that interval will include the population mean. So let's take a moment here and we'll figure out how we can compute that confidence interval. In order to do that, we first have to decide how confident we want to be. So let's imagine that we wanted to be 80% confident. What range of values would you use if you wanted to be 80% confident that the mean was in the middle? So let's say that this is your sampling distribution here, and you go to your t-table B.2, and you use degrees of freedom 8, because remember, there were 9 infants in this sample. And you go figure out what is the z-score that binds the lower 10% and the upper 10%, or a combined 20%. A combined 20% in both tails. Hopefully you're able to discover that it was negative 1.397 and positive 1.397. How did we find that out? Because remember, if you go to the degrees of freedom 8 and you figure out 20% in the two tails combined, and you find with the intersection between those two, it's 1.397, and that would be negative 1.397 on the negative side and positive 1.397 on the upper side. But let's say instead that you wanted to use 90% as a criterion, that you wanted to be 90% confident that the mean was in the middle of that range. So this time we'll use the same degrees of freedom 8, but let's go back to that table B.2 and figure out if 10% of the 10% of the population were in the combined tails. Hopefully you found that the answer was negative 1.86 and positive 1.86. You should see here that the reason for that is if we have 10% in the two tails combined, and we follow this down till we get to the row that says degrees of freedom 8, the intersection there is positive and negative 1.86. So, the formula for computing confidence intervals is based on the t formula. If you take this t formula, mean minus mu over standard error of the mean, you can algebraically rearrange the equation to solve for mu and say we're trying to figure out where the actual population lies. And if we have the mean and the t-score and the standard error of the mean, then we're able to compute where the population mean likely lies. In this situation, though, this t is not the computed t that we used before. This is a critical t. So I'm going to put this little alpha symbol here to recognize that this t is your critical t that corresponds with the 10% or the 20% in the tails, or whatever it is that you've decided is your level of preferred confidence. And so in your formula sheet, you'll see that the confidence intervals formula looks like this. It's the mean of the population equal to the mean of your sample plus or minus the t alpha, the critical t. So that's how you can say that. This isn't t alpha so much as we could say the critical t that's associated with whatever percent of confidence you want to have. and then you multiply that by the standard error of the mean, which is what we computed before. Okay, so in order to compute your confidence intervals, we're going to rely on a bunch of things that we've already computed long ago in the module. Remember, we have 9 infants. They're staring at attractive faces for 13 seconds. They've got a standard deviation of 3 and a standard error of the mean of 1, and we've computed the t as 3. If we pick the appropriate degree of confidence, that might be, 80, 90, 95, 99? Usually it's 95%, but this time we'll use 80%, and you could choose any percent you want, because the degree of confidence is how confident you want to be that when you finish computing this interval, the mean of the population actually falls within it. So we're going to use 80% here just for illustrative purposes. We use the t-distribution table to find the value of t. Remember, this is the critical t, not the t you computed. It's not this t. It's the critical t from the table. So for our infant study, the degrees of freedom was 8. The confidence interval for the alpha was 0.2 because we're using an 80% confidence interval. So the alpha is 0.2. And then we therefore say that, and remember, this is across 2 tails. So then we have to find what's the critical t. Go ahead and take a moment and see if you can find that in your table again. We just did it a moment ago. Hopefully you found that that was positive or negative 1.397. So we solved we solved that rearranged t equation. We found this in our formula sheet. It's the mean of the population equals the mean of the sample plus or minus that critical t times the standard error of the mean. And we know all of this information now. We computed we found the t in the table as 1.397, so we put that in. The mean of the sample was 13 seconds as indicated up here, and the standard error of the mean was 1, also as indicated up here. So if you put those in, you've got 13 plus or minus 1.397 times 1. And if you carry this through and you take 13 plus that and 13 minus that, then you should end up with an 80% confidence interval that ranges from, you could take a second if you want and compute on your calculator, 11.6 up to 14.4. This is the range in which we can be 80% confident that the population mean falls. If we computed sample after sample after sample, and we computed a confidence interval for each one of those samples, 80% of the confidence intervals that we computed for 80% of the samples would actually include the true population mean. Now, just to make sure that we're clear what this is really saying, we think that infants spend 13 seconds staring at attractive faces out of 20 seconds possible. Now, if we had every single infant in the whole world undergo this research study and stare at attractive faces and unattractive faces for a total of 20 seconds, we think that infants in the population would probably stare at attractive faces for about 13 seconds, but we don't know exactly how long they would stare at attractive faces because, as you recall here, the population mean is never exactly the same as your sample mean. That's the principle we've been talking about since Module 1, sampling error. Because of that difference, because we're never quite sure exactly what the population mean is, we have to make a guess. And we think it's about 13, but it might be somewhere as low as 11 and somewhere as high as 14. But it will probably be between these two values. If we actually did measure every single infant in the whole world and make them do this research study and have them stare at faces, then the actual mean of how long those children would spend would probably be somewhere in this range. Close to 13, maybe not exactly 13, somewhere in that interval. That's what a confidence interval is. There are certain factors that affect the width of your confidence interval, how wide of a range that number is. Like in this example, it ranged from 11 to 14, but it could range bigger or smaller depending on decisions that you make. So I want you to take a moment and consider what factors would you consider when deciding on a confidence level. For example, why would you choose 80% versus 95%, or vice versa? Pause your video and think this through for a moment. The confidence level that you desire to have will depend on two things. If you want to be more confident that your interval includes the actual mean of the population, then you've got to increase the interval width. So if you want 95% instead of 80, then your width is going to have to be wider. If you want to have a smaller, more precise interval that more accurately estimates what the population mean probably is, then you're necessarily less confident that the true mean is included in that interval. So if you had a 95% confidence interval, it would be wide like this because 95% of the time, the true population mean would fall somewhere in this range. If you had an 80% confidence interval, then it would be smaller. Only 80% of the time would it actually capture the population mean. Sometimes it would be a little outside on either the upper or the lower end, and you couldn't be as confident that you've got the population mean. But because it's narrower, you're more precise about your range. This is difficult to explain, but what I'm trying to communicate is if your range goes from 11 to 14, that's one thing. But if you had to say the range that captures 99% of the captures the population mean 99% of the time goes from like 4 seconds all the way up to 18 or 19 seconds, that range is so wide that it would be useless to say anything about the actual population mean. You'd say, well, infants look about 13 seconds at the attractive faces, but it could be as low as 4 seconds or as high as 19 seconds. That doesn't tell anybody anything useful. You have to have a narrow enough range to be useful. Like between 11 and 14, that's useful to say we think that it's somewhere in that range. But necessarily, if your range is narrow, then your confidence has to be lower because you're going to capture the population mean less % of the time. The sample size also impacts the width of the confidence interval. If you have a larger sample, then you're going to have a smaller interval. If you have a smaller sample, it's a larger interval. Why? Remember back when we were doing this online module where we saw that that if you took a population and you drew sample after sample after sample of just 5, so a very small sample, and you computed the mean of each one and you plotted it into a sampling distribution, then the sampling distribution ends up being wide. But if you take larger samples like 25, then the the sampling distribution ends up being much more narrow. And the reason for that is because each one of those samples, because it's larger, is a better reflection of the actual population. And so each one of those is closer to the population mean. They're a better representation. So if you have larger samples, then your confidence interval will be more narrow, suggesting that it's easier to guess what the population mean is than it would be if your samples were smaller. So, finally, in the literature, last step what we need to do is we write a sentence, and that sentence has to include quite a bit of information now because the statistics that we've computed are growing. So the infants spent an average of 13 seconds out of 20 seconds looking at the attractive face with a standard deviation of 3. Statistical analysis indicates that the time spent looking at the attractive face was significantly greater than would be expected if there were no preference. And then when we list our statistics, we have to put the t here, followed by, in parentheses, the degrees of freedom. After the t, we say that equals whatever it really was. It was 3. And we put another comma. The p is less than 0.05, or if there was no difference, then we'd say the p is greater than 0.05. And then we put a comma, and we write here either the d or the r squared. I've listed the r squared, but you could just as easily have put the d because we computed the d. So here the r squared equals 0.5294. And then we put another comma, and we also include the confidence interval. So the 80% confidence interval, CI for confidence interval, is, and then in brackets, square brackets like this, we put the range. The lower end comma, the upper end, end bracket, period. So this is what a sentence needs to sound like when you've computed all of these statistics. I recognize that this is a little daunting, but the formula for this sentence is actually pretty straightforward. We start with the descriptive statistics up here, the mean and the standard deviation, and then we move it to the inferential statistics. We're drawing inferences about the population based on a sample. These statistics come next. So inferential statistics come next. We write a sentence that describes what we found. In this case, we found that the infants spend longer looking at attractive faces. And then we put the T, degrees of freedom, the P, an effect size, and the confidence interval. If you haven't computed all of these things, then you don't include all of these things. You just include what you've computed. And you'll know what to compute because in every homework and in every test, I'll tell you what I want you to compute. You should, in real life, use the exact p-values. Sorry, that's pointing to the wrong thing. Use the exact p-values when it's available. For example, if you're using a computer-to-computer statistics, it might tell you that the p equals 0.017. And so you would say that p equals 0.017 instead of p less than 0.05. Now, we've worked through the entirety of a t-test. Congratulations! Woo! If we had a directional hypothesis, we would need to use a directional test. That's a one-tailed test. You recall doing this in our previous module. If we have a directional test, we would follow very much the same procedure, but it would differ in that the alpha would be slightly different, and the critical region would only appear on one side of the distribution rather than both. So I'm going to demonstrate using the same example of infants from before, what this would look like if our hypothesis was a directional hypothesis, that we thought the infants would spend longer looking at the attractive faces. So we state the null and alternative hypotheses like this. The alternative hypothesis states that attractiveness will cause the infants to increase the amount of time they spend looking at the attractive face. And the null hypothesis is that the predicted effect will not happen. So when you're using a directional test, it's easier to actually start with the alternative hypothesis because it makes more sense to us. So the alternative is that the mean amount of time that we spend looking at attractive faces will be more than 10 seconds because we like looking at attractive faces. And then you just make the null hypothesis the opposite of that. So instead of being greater than, we make it less than or equal to. So if it's exactly 10 seconds or if it's less than 10 seconds, then that will mean that people don't like looking at attractive faces as much. Remember that we've already computed a bunch of stuff, so I'm just going to keep that up here. We're going to set an alpha level and locate the critical region using the t-distribution table B.2 and the degrees of freedom. So remember that the population mean is 10. In this situation, we don't know the population standard deviation, so we're going to guess it based on the sample standard deviation of 3. And we can compute from that a sampling distribution. The sampling distribution has a mean of 10 as well, just like the population. But the standard error of the mean we've already computed is 1. We transform the entire sampling distribution into t-scores with a mean of 0 and a standard deviation of 1. And then, this time we're going to use an alpha of 0.01 just for fun. So let's look at what it would be like if we put 1% of scores in the tail. What would be the t associated with 1% in one tail? Remember, the degrees of freedom in this sample is n of 9 minus 1, or 8. So we look at the t-distribution, and we find the two-tailed test with an alpha of 0.01 and degrees of freedom of 8. Pause your video, figure out what that is. Hopefully you found that that was plus or minus 2.896. That we're using here to demark out the highest 1%. And just to remind you how we found that, we come to the degrees of freedom 8. We find the proportion in one tail that is 1%, and where that intersects is 2.896 right there. We calculate the t-statistic, but this is actually the same as what we already computed, so really only the alpha level is changing. So you'd go through the same procedure as as we did already earlier in the module. You find your t is 3, woo! And then we plot it in the null hypothesis distribution. If we have this as our distribution with a critical t of 2.896, we plot it in the distribution, it's around 3, and because it's in the critical region, then we reject the null hypothesis, and we write a sentence like, the time spent looking at the attractive faces was significantly greater than would be expected if there were no preference. Then we list our t with degrees of freedom, and then we list our p less than 0.01 because we use that alpha. And then we say, again, one-tailed, because whenever you do a one-tailed test, you have to specify that that's what you did. But you don't have to specify a two-tailed test because everybody just assumes by default that that's what you've done. Whew! Take a breath. My goodness gracious, this was a long module. Just to recap, the t-test that we covered in this chapter is called a single sample t-test. The reason for that is because we've drawn a single sample from the population. We've done something to it, given it some kind of treatment, or measured something about it, and then we've compared it to the original population, or we've compared it to some hypothesized population, like the whole 10 seconds thing that we did in this module. We are then comparing our sample against a known or hypothesized population mean. This kind of test works well for known population means, like a standardized test with a mean of 80. And it also works well for hypothesized values, like in this case we did this like 10 seconds thing spent looking at attractive faces. But we would use a z-test if we knew the population standard deviation. The reason why we're using this t-test here is because we don't know the population standard deviation. So we used this instead of a z-test because we didn't know the standard deviation of the population, and we had to estimate that parameter, that population statistic, from our sample. A z-test is good for things like IQ or SAT, where we know both the population mean and the standard deviation. Now that you've learned all this stuff, I want you to go ahead and work through this practice activity where a researcher wants to know whether moving from home to home to home as a child impacts your well-being as an adult. She obtains a sample of 12 young adults who moved 5 or more times before the age of 16. That's kind of a lot of times, right? And gave them a standardized well-being questionnaire. And in the population, that has an average of 40. So if you just look at everybody's psychological well-being in the population, you'll see that they have an average of 40. But her participants had the following scores, and they're listed there. So what I want you to do is compute the mean and standard deviation and see, is that different than 40? If it's lower than 40, that means that that moving around from home to home as a child made you have poorer psychological well-being. If it's higher than 40, it means it's actually beneficial to move around when you're a child. So compute the mean and standard deviation, then write the null and alternative hypotheses, find your critical t using the two-tailed test with alpha of 0.05. Calculate your t-statistic, make a decision. And then after you've done that, also compute and interpret the effect size. In this case, I'll just have you do Cohen's d. And calculate the 95% confidence interval. Once you've done all of that stuff, write a sentence as if for publication. And this practice exercise will look exactly like what your test is going to look like in a few days. Please pause your video, work through this. When you're finished, I'll show you the answer. So go ahead and resume when you're finished. The average we computed from those scores was 37. The standard deviation is a formula that's obtained from your formula sheet. You need to know this because I told you to compute the mean and standard deviation of the sample that she's drawn. But in order to compute the sample, you have to know the variance. In order to compute the variance, you need to know the sum of squares divided by the degrees of freedom. So you figure out the sum of squares first, because we're working backwards to find the standard deviation. So first you take the sum of x squared minus the sum of x squared divided by n. That should yield you 118. You can plug in that 118 for the sum of squares up above. Remember that the sample size was 12, so you should have a degrees of freedom of 11. You plug in those values and you get a you get a variance of 10.73. You plug that into this formula, take the square root of it to get a standard deviation of 3.28. The first step of a hypothesis test is to write out the null and alternative hypotheses. So the mole of the mean of those who moved around a lot when they were kids is equal to 40 if it doesn't have any impact. The alternative hypothesis is that the mean of those people who move around a lot is something other than 40. It might be greater than or less than. Now, maybe in your example, you thought that this was a directional test. If you go back for just a second, you'll see that we're asking the question using a two-tailed test. Does it have any impact? So, two-tailed test yields you a null hypothesis where the population is a 40 and a sampling distribution of also a mean of 40, but because we don't know the standard deviation of the population, we don't also know the sampling the standard error of the sampling distribution, and so we have to compute that based on the standard deviation of the sample. So the standard error of the mean for this sampling distribution is the standard deviation divided by the square root of n, which we compute as 0.95. That right there is the standard deviation of the sampling distribution. You transform all of that into t-scores, which have a mean of 0 and a standard deviation of 1, and then we mark out our critical region. The way we do that is we go to the table and we figure out from table B.2 what are the z-scores that bind the lowest 2.5% and the upper 2.5%, because we're using that 0.05 alpha. If you look at the proportion in two tails combined for 5%, you come down here to a degrees of freedom of 11. You'll see that it's 2.201. So you mark those on your distribution here, and then you compute your t. The t is the mean of the sample, 37, minus the mean of the population, 40, divided by the standard error of the mean, which we computed at 95, and that yields negative 3.17. You plot that in your null distribution down here as a t-score that is about a little over 3 standard deviations below the typical mean that you might expect, just by chance, to find of the psychological wellness in the population. So these people are far worse off than people who have not moved around a lot as a child. So we reject the null hypothesis. Then, to compute Cohen's d, you take the mean of the sample minus the mean of the population. Again, that was 37 minus 40, and you divide it by the standard deviation that we computed on the last slide. You get a 0.91. Remember, we've got this table that tells us how to interpret Cohen's d by in terms of its size, and this right here looks to be even greater than what we call a large, and so this is a large effect size. If you interpreted this in terms of what it really means, then you would say the folks who moved around a lot as a child are about 0.91 standard deviations lower on mental health or well-being than everybody else in the population. So that's quite a bit lower. Nearly a whole standard deviation lower than the rest of the population. We compute a confidence interval using that formula that we found in our formula sheet. You take the mean of the sample, 37, you add plus or minus the critical t that's associated with that 95% confidence interval, that's 2.201. You multiply it by the standard error of the mean, and you get 34.91 or 39.09, depending on whether you're talking about the lower limit or the upper limit. Then when you write your sentence, you say something like, the people who moved a lot during their childhood had an average well-being score of 37 with a standard deviation of 3.28. This was significantly lower than the general population, which has a mean of 40, suggesting that moving frequently as a child has a negative impact on adult well-being. And then you list your t-score with the degrees of freedom in parentheses. It was negative 3.17. You put your p-value after that, your d-value after that, or your r-squared if you computed that, and then your 95% confidence interval, which ranged from 34.91 to 39.09. All right, hopefully that was helpful for you. Hopefully you were able to practice through that, and I strongly recommend that you spend a lot of time working through examples like this in advance of the test so that you know in any given situation how to especially remember how to work backwards. If you're looking for a t, just look and see the bottom of the t formula says that you need to compute the standard error of the mean. So then you go to find the standard of the mean, and when you find that, then you recognize, oh, I need to find the standard deviation. And in order to find that, then you go compute the standard deviation as the square root of the variance, and then go to the variance, and you figure out, oh, I need to figure out the sum of squares, and you just keep working backwards. If you need the t, then just work backwards until you figure out what's the thing you know to know how to compute, and then work forwards again until you find the t. Goodness gracious, that is a lot of work. I hope that it was helpful, and I hope that if you have any questions, you'll reach out to me and pose them, because I'm always willing to help mentor students through this admittedly difficult material. So good luck.